Alright, so waves. Light, waves. Yes, yes! I love waves. I don't. Waves suck. This is the word. I hate waves. Whatever. Man, whatever. So, waves. Light is a wave. And waves are different to particles because they have different properties, different this, different that. And we're going to talk about it. And the first thing that we're going to talk about is interference. What is interference? Interference is when waves interfere. Yeah. Basically, it's when we have one wave, let's say from here, this is the starting position, and let's say I shoot a wave like that, and it goes in this direction, and I shoot another wave, actually, let's make it even simpler, just like that, on a string, like that, and on this side, I have another wave, like that, and this guy's going that way, this guy's going that way. Interference is when the two waves going in different directions collide, and they'll either constructively interfere, which means that their amplitude will combine and increase, or they will destructively interfere, which is when their amplitudes will cancel out. Well, they'll still combine, but they'll combine into zero, which will just cause a flat line. This is constructive, and this is destructive. Now, let's have a look. I've got a simulation. Let's see. As you can see, this wave... Yo, can I pause, please? Oh, never mind. So, we have a wave, a negative wave, as you might say, and a positive wave. And as you can see, they both have the same height or the same amplitude of 3 and 3. And when they interact with each other, as you can see, this is a bit off, but whatever. Yeah, as you can see, they interfere and it results in a flat line because the waves have cancelled out. But if I change it to this, you can see now the waves go towards each other in two different directions and make an even bigger wave. What? That's interference. It's simple. It's easy. Not too shabby. Let's go back. Interference. One thing to remember about waves is this formula. V equals F times lambda. Up here I've put it. And F times lambda, frequency times lambda, equals the velocity of... Anyway, sorry. Where was I? Velocity is in meters per second, as we all know. Meters a second. This is in hertz, and this is in meters. And what's good about this is that it applies to, I'm pretty sure, every single wave. So using this will allow you to relate them to all these different functions, allow you to solve for each one. You should also remember F equals 1 on T. So you can replace F if you don't have F, because V also equals to lambda on T. Awesome. And that's standing waves for you. But now, that's not standing waves, because I'm about to explain standing waves on the next page. So what is a standing wave? Well, a standing wave is a wave that stands. It's actually a wave that looks like it's not moving. Waves usually go like this, right? And then they'll oscillate, boom, 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 like that, like this. Basically, just like this, you know. So let's look at it. Look at it move. Look at it move, and it keeps going. It's a wave, but a standing wave is different. This is a standing wave, and as you can see, it looks like it's not going anywhere. Like, see, it just goes up and down and up and down. But you can see these red and blue waves. What do they mean? Well, what's actually going on here is that this red wave is being emitted and is traveling in this direction. And when it hits the wall, it bounces and reflects, creating the blue wave. As you can see here, the blue wave goes in the opposite direction with the same amplitude, creating the standing wave. Okay. When these standing waves are created, there'll be these things called nodes. Nodes and antinodes. A node is the absolute minimum. Like, they will never move. As you can see here, these ends represent nodes. And look, it's not moving. Even when this guy moves, it stays the same. And these antinodes have maximum and minimum amplitude, right? They're right smack dab in the middle. And yeah, those are very important. Nodes, antinodes. You can remember antinodes, or you can remember nodes as in no displacement, antinodes as in no displacement, which means displacement. But it's up to you how you remember it. Now, question time. The thing about standing waves in VCE physics is that it's usually between two stationary points. And the thing is that when there's two stationary points, there's only really a certain amount of like frequency that is able to be put together in between like a length. This is possible, like a standing wave like this is possible, but this, let me put it in a different color. This is not possible because it is exited the allowed length. As you can see here, it's exited it, and if you emit it from here, it'll mess it all up and it won't look good. So let me just, so these are what are called harmonics, and harmonics just another way to say standing wave. But the thing about harmonics is that they're very special. Like I just said, they can only be certain harmonics for certain lengths. And this is what's called the second harmonic. And each one has a name. Each one is like first, second, third, blah, blah, blah. And you can tell it's a second harmonic because it has two antinodes. One here and one here. Because these guys have maximum and minimum amplitude. Maximum, minimum amplitude. So this is the second harmonic. And the first harmonic looks like this. That's really bad. But look, as you can see, one antinode. Maximum, minimum. Maximum, minimum. This is the first harmonic, also known as the fundamental. No, it's just called the, I think it's called the fundamental harmonic. I don't know. But the thing about this is that the frequency in the first harmonic is called the fundamental frequency, and it's denoted by F1, F base 1. And the good thing about this is that these guys are all just multiples of the first harmonic's frequency. So if this guy had a frequency of 100 hertz, then this guy would have 200. Because you just do n, which is the numbered harmonic, times the fundamental harmonic, or fundamental frequency, giving you 200 hertz and F base n. Now, Sometimes you're not going to be given the fundamental harmonic, fundamental frequency, and that's okay, because all you have to do is use this formula. F equals NV on 2L. L is length in meters, and this is meters a second. Easy peasy lemon squeezy. And then length again is referring to this length, n times lambda on 2. Lambda is the wavelength of the harmonic in meters, and n again is just the numbered harmonic that you're measuring the wavelength from. And that's basically it. That's it. That's harmonics and interference. There's probably a bit more I haven't covered, but you know, you got it. You got it. And that's it. Good job.